Nicholas, I cannot hear your...
Can you hear me now?
Good.
Muy buenas tardes a todos los asistentes. Daremos inicio a la conferencia en este momento. Como es de su conocimiento, hoy tenemos la conferencia Exploration for Epithermal Gold Deposits a cargo de Jeffrey Hedenquist. A manera de una breve biografía, Jeffrey realizó investigación en desarrollo de energía geotérmica con la División de Química del DSIR de Nueva Zelanda y en descargas volcánicas para el Servicio Geológico japonés durante 10 años. También estudió la formación de depósitos epitermales de oro y pórfidos de cobre. Desde 1999 se desempeña como consultor independiente para la industria minera, varias agencias gubernamentales y el Banco Mundial, proporcionando asesoría en proyectos de cobre y oro hidrotermal en más de 40 países, así como en la capacitación relacionada a la exploración mineral. Dentro de su trayectoria educativa, se tiene que es geólogo del Macalester College, posee una maestría de la Universidad Johns Hopkins y un doctorado de la Universidad de Auckland. Fue presidente de la Society of Economic Geologists y en la actualidad se desempeña como profesor adjunto de la Universidad de Ottawa en Canadá. La conferencia tendrá una duración de 50 minutos a 1 hora. Posteriormente tendremos una sección de preguntas, que podrán hacerlas por Zoom mediante la caja de preguntas y respuestas y mediante el chat en vivo de YouTube. De ser posible, escriban sus preguntas en inglés. De lo contrario, si las hacen en español, las preguntas deben ser lo más claras y objetivas posibles para facilitar la traducción y agilizar la sesión. En el chat les dejaremos el link de YouTube para que difundan a quienes no alcanzaron a entrar por Zoom y les recordamos que pueden descargar las diapositivas libremente hasta el 31 de mayo. También les queríamos contar que justo desde las 10 en Colombia y hasta estos momentos tuvimos el encuentro iberoamericano virtual de capítulos estudiantiles de la SEG, organizado por la Universidad Nacional de La Plata en Argentina, con la participación de capítulos de Argentina, Chile, Perú, México, Colombia, Ecuador, Brasil y España, no sé si alguno se me quede, generando enlaces para posteriores actividades y sobre todo en estos tiempos de cuarentena. No siendo más, that's all the introduction. Jeffrey, thanks for your time. The space is all yours, and please go ahead with the conference.
Okay, thank you, Nicholas. I will share my screen. Can you see my screen, Nicholas?
Yes, I'm watching it.
Okay, very good. So, again, thank you, Nicholas, and thanks to the chapter.
Can you please put full screen mode?
Okay, I'll do that. Thank you. Yep. Thanks to the student chapter in Bogota, as well as to the SEG for assisting in this presentation. And my talk today will be on exploration for epithermal gold deposits, but specifically one style that's responsible for about half of the world gold production of epithermal, not all production, but half of the epithermal production. One example would be here at Salares Norte in Chile, which was recently discovered and will come to at the end of the talk. Now, the topic is discovery versus dogma. How are deposits discovered? And unfortunately, where does dogma get in the way? Now, I'm not going to be blaming anyone. We all have our own beliefs, dogma. And as a result, we have to learn to keep that dogma somewhat aside and really just make observations. Look at what the rocks are telling us. So here I'm going to first outline, and this outline is also a summary of what I'll be saying. Basically, I'll start with looking briefly at magmatic-hydrothermal systems that are intrusion-centered. Specifically, the formation of a vapor phase, a magmatic vapor phase, coming from porphyry depths, intrusion depths of a couple kilometers, and that vapor condenses near the surface to form very acidic condensates that cause advanced argillic alteration. One style of advanced argillic alteration, those of you who attended Antonio Ribas's presentation on the 4th of May knows, in fact, there's 5 environments of advanced argillic alteration. Here we're going to focus on one and a little bit mention of 2 others. And then discuss the relationship between this shallow advanced argillic alteration, which forms, as Silito defined, a lithocap. It'll be important to note that during formation, this lithocap is sterile. It's basically barren in metals. But in some cases, it will subsequently be mineralized with metals that are introduced during the chlorite-cerussite stage of the underlying porphyry. We'll briefly look at that as well. The main part of the talk will be looking at examples of ore deposits that have been discovered, many of them having been discovered by the 2nd, 3rd, 4th company rather than the first. But there's also some cases where it's in fact the first company that makes a discovery. And regardless, whoever discovers it usually has a good geological understanding of what they are looking at. And finally, my conclusions, very simple, is that we should not be trying to force prospects into any theoretical model. We need to really look at the rocks, use some imagination, some lateral thinking to help us focus on targets. Okay, before we get into the ore deposits, let's start at the sort of the tectonic scale. And this shows a diagram, very schematic, of 2 arc environments, one oceanic, the other continental, in which both epithermal and porphyry deposits can form. There's also another environment of formation of epithermal in the back arc or in extensional zones. I'm not going to be talking about that today, but it does exist. It is important locally. And epithermal was argued to be related to porphyry for a long time, but now we know very, very well that there's very direct genetic relationships, as I'll discuss in a moment. Now, various names have been put on these different environments of epithermal, and one set of names, high, intermediate, low sulfidation. You know, what I'm going to stress is that names are not important. If you don't understand what these terms mean, or if you don't like the terms, well, let's just call the epithermal group a basket of fruit. And these could be apples, manzana formed in extensional environments versus grapefruit and oranges formed in arc environments. Now they're all fruit in this basket, but grapefruit and oranges are more closely related genetically because they're both citrus. So a bit similar in epithermal. They're all epithermal, high and intermediate sulfidation are more closely related to one another. Okay, why is it important? Well, sometimes, as you can see here, some things don't make sense. Is this actually a apple skin that's overprinting a orange inside? Or is it perhaps some genetic variation that we don't quite understand? Well, first we have to know the end member characteristics. And that's why it's essential to describe the characteristics of the prospect we're looking at. And again, names are not so important. It's the observations we make. This section shows a schematic simply called porphyry systems, porphyry copper systems. Well-known paper now by Dick Silito in 2010. If you haven't gotten a copy, I highly recommend this paper. And the reason that Silito called it a system is that he's not looking at just only the porphyry copper deposit at depth, but also he's looking at, he's considering the alteration that's involved around the. Oops, sorry, Monica, I'm getting some feedback here from you. He's looking at the alteration associated with the porphyry. He's looking at this shallow level of advanced argillic alteration, which is up in the lithocap. Also considering a variety of ore environments, porphyry copper, but then also carbonate replacement, either skarn or replacement deposits, and then the epithermal environment, which is roughly the upper kilometer or so. Both are lithocap hosted high sulfidation deposits, as well as potentially on the margins, intermediate sulfidation veins, gold, silver, or silver gold, sometimes with base metals. Okay, now in this environment, this is intrusion centered. We're very close to a dome field perhaps, and there can commonly be lacustrine beds nearby filling craters. Let's take a look now at what one of these environments might be near the surface. This is White Island, unfortunately recently erupted in New Zealand, killing some tourists. But back in 1988, it was discharging continuously high temperature magmatic vapors and gases. But then some years later, those vapors condensed into a very acidic crater lake, pH 0.2. And as that acid fluid flowed off to the ocean, it dissolved the andesitic host. The acid stream was slightly less acid, pH 6, and all of these precipitates you can see here, that's basically dissolved andesite. Back in the crater lake, this sort of gray crater lake, there's a lot of colloidal silica in suspension, but at some times that colloidal silica settles out of suspension and forms finely laminated deposits, as we can see here. That's a 10 centimeter scale bar there, 30 centimeters in total. Well, why is this important? Why am I talking about colloidal silica and crater lakes? Well, let's go take a look at Yanacocha, the world's largest epithermal high sulfidation district in the world, production of at least 1,200 tons of gold. In this case, Chilean is a dome, and Rayleigh Dome, you can see the vertical flow banding in this inset to the right. And if we go onto the margins of the dome, we see these finely laminated siliceous deposits, no rock fragments, just siliceous deposits. And there's even some cross-bedding here. You can see the pointer and the magnet cross-bedding, basically telling us that these siliceous sediments were deposited sublacustering. This was an acid crater lake right around this dome. And so we know that that was basically paleosurface at the time of formation of these deposits. Well, as Tony Longo and others at Yanacocha showed, there are other deposits of these finely laminated siliceous deposits. They're not silica sinters, they're finely laminated siliceous colloidal silica, even some drill core, and they indicate very shallow erosional conditions. Well, basically the interpretation is that this dacite dome had an acid crater lake around it, depositing these siliceous sediments. Okay, another environment, active environment of these formation of these acid condensates is here at Satsuma Ujima, just south of Kyushu. And there are 800-degree vapors with SO2 and HCl discharging. Those vapors condense, and the condensate reacts with the rock. We can see extensive alteration near the edifice of this 1,000-year-old Rayleigh Dome. And the leached solutions flow off to the ocean. Here we have pH 1.5 springs flowing into the ocean with dissolved rock components. The reactions are the magmatic volcanic SO2 disproportionates or mixes with water to form sulfuric acid. And then the sulfuric acid and the hydrochloric acid from these magmatic vapors, then those acids start to dissociate at lower temperatures. They start generating hydrogen ion, and it's the hydrogen ion that reacts with the rock. Well, here we see up near the summit, we see this rhyolite, that's been altered here by these condensates, acidic condensates. This rhyolite contains up to 97% silica. So obviously everything else in the rock, sodium, potassium, calcium, also aluminum and iron, have been leached away. And we're left with this residual quartz, but it's barren, as you can see, maximum of 29 ppb, parts per billion gold present. There's also other minerals forming on the margins, alunite and clays, etc. So this is the environment of formation of these lithocaps. So now you can see why I started off with a few of those views. Here we're on the flanks perhaps of a dome when it was active. There may have been acid condensates. They're responsible for formation of these, this alteration. Now let's take a look at what's happening at depth. The magma intrudes, a shallow dome or a dike intrudes, and then magmatic fluid exsolves. It's a intermediate salinity fluid. Here, particularly with high copper, we can see the tetragonal chalcopyrite crystals here. But as it reaches within about 2 kilometers or so, that fluid hits its solvus, it separates to hypersaline liquid or a brine, very saline brine, about 50% salinity. Here's sodium chloride, potassium chloride, sylvite crystals, hematite, etc. Separates to brine and vapor. Now the brine is very dense, it stays at depth, it's responsible for forming biotite and Cape feldspar alteration, potassic alteration, but there's a vapor formed. That vapor, low density, means it's very buoyant, and the vapor discharges just like we saw from White Island and Satsuma Iwajima. But some of that vapor condenses, as we also saw at those active volcanoes, condenses and forms this pH 1.5 condensate sulfuric acid, hydrochloric acid. Proximal to the vent, it leaches the rock, leaves residual quartz, possibly vuggy, but again, barren, with halos of quartz alunite or quartz kehlnite. Subsequently, as the magmatic system is cooling, we start to have an overprint of chlorite cerussite alteration, or white mica. And at this stage, the fluid at the lower temperatures that's exhaled from the magma does not separate to brine plus vapor. It does not intersect its solvus. So it rises and overprints the top of the porphyry with this white mica alteration, but that fluid may enter into the porphyry, or sorry, into the lithocap because it's less dense. And if it does, it's responsible for depositing the enargite and gold. If in fact that does not rise, we're left with a barren lithocap, even if there may be a porphyry deposit having formed at depth. But all is not lost because that same white mica fluid may rise along structures to the margin of the lithocap and form intermediate sulfidation epithermal veins. Okay, so this is sort of our general understanding. Let's now take a look at a well exposed and also well-studied high sulfidation epithermal deposit in the Philippines, in the Mancayan district, northern Luzon, where there's also an underlying porphyry that's been discovered. And here we see this lithocap, quartz alunite lithocap, very resistant to erosion. So it forms these cliffs. And as we go to the northwest, we see more cliffs here. And that's because all along a unconformity between the volcaniclastic basement and the overlying pyroclastic rocks, there is permeable horizon, and the acid condensates at the time of formation, the acid condensates have leached the rock and left this quartz alunite lithocap. So let's take a look at a cross section through that unconformity up here to the northwest. And we can see the underlying volcaniclastics shown here, overlying dacite pyroclastics, and right at the unconformity is where the residual quartz and also the quartz alunite that outcrops that has formed along this unconformity. Now again, the quartz alunite is resistant to erosion. It forms these cliffs we can see. They've been exposed because of erosion by the river valley and through here, so they're exposed. Now, if we recognize this alteration and we say, well, let's drill test this, we go up to the top of the hill, set up our drill rig, drill a vertical hole. We will penetrate this kaolinite dickite alteration, then get into the quartz alunite, as well as residual quartz and gray, but we'll drill out of it very quickly. It looks like a rootless lithocap. However, there are never rootless lithocaps. In this case, what we would do now is to map the area, get an idea for the stratigraphy, and realize that this is a lithocap forming along an unconformity. And knowing that all lithocaps have feeder zones, we look for any major structure, fault, dome margin, etc., diatreme perhaps, that may have provided vertical permeability. And in this case, a young volcanic unit here has been offset. Well, that's possible, one feeder zone. If we drill test that, well, we would have been very successful in identifying the feeder zone with very high grades, several percent copper, 5 grams or more gold, much higher than off in the distal part of the lithocap. Okay, so 70% of the ore here at Lepanto was recovered from that feeder zone. So here's a map of alteration, geologic map, but also this is alteration from a variety of colleagues, and Joey Garcia, Zhaoshan Chang, etc. And what this shows is that along the unconformity here, with the river having eroded into the basement, along that unconformity is this lithocap of quartz alunite, some silicic alteration as well, but mainly quartz alunite. And notice the scale there, 7 kilometers, very extensive. However, in the sample, in the mapping here with quartz alunite above and below the, dickite kaolinite above and below these quartz alunite cliffs, at the same time, collecting samples, we find that all of the quartz alunite has basically less than 50 ppb gold anomaly, essentially barren, as low as about 12 ppb. So what does that mean? Well, some people might say, well, you know, this is a barren system, let's walk away from it. But what are some of the features here that's suggesting we should stay? Well, as I already mentioned, this is a huge district with classic, typical quartz alunite lithocap style alteration for 7 kilometers. Also, there are some occurrences, very scattered. There are 4 occurrences here of 1 to 4 grams gold in narrow silicic structure, with the most significant along this big structure here that the Spaniards mined, and before that, the Igorot Indians mined for the luzonite, typocalative of luzonite in the island of Luzon, mined it for the copper, but also there was a little bit of gold there, although the gold was not of interest back in the 1600s. Well, in addition, one other feature is right here, there's a fragmental deposit from a diatreme, and it contains porphyry copper clasts. So suddenly we see everything is here. We've got the large lithocap of quartz alunite alteration. We have silicic structures that do locally have some gold mineralization. We also know that there must be a porphyry copper at depth someplace because of the class, the diatreme deposit at the surface. Well, fast forward, and those Spanish workings were right here, just the tail of the basically blind Lepanto epithermal deposit that produced about 1 million tons a million tons of copper and 100 tons of gold. Subsequently, discovery of the far southeast porphyry deposit, 900 million tons at about 0.5% copper, 0.7 grams gold, and with previously discovered smaller and lower grade porphyry deposits in the area, Ginong, Mohong, Buaki, and subsequently in only 1992, discovery of the Victoria and Teresa epithermal veins, intermediate sulfidation. So very complex district, everything happening here. Now let's take a look at this long section through this system here. And we see in green the volcaniclastic basement, the intrusion of, then the subsequent deposition of the Imbagila dacite about 2 million years. Here's the unconformity. We even see the volcanic necks in through this area. And subsequently, at about 1.45 million years, coarse diorite porphyry dikes intruded, and those dikes are what formed the far southeast porphyry. Now, a beautiful lavender style of quartz veins with chlorite and white mica halos, responsible for introduction of most of the copper as chalcopyrite and some bornite. And here, drilled out by Goldfields in the 2013-2014 with about 100,000 meters of drilling from the 700-meter level here. Of course, it was discovered beforehand, but it was drilled out, the resource was drilled out subsequently in a modern resource reserved estimate. And here we can see the 0.7% copper grade shells, the 1 gram gold grade shells in yellow, and some distal moly grade shells. There's the porphyry at depth and the high sulfidation Lepanto and Nargite gold deposit along the unconformity, but within the plane of the Lepanto fault. Well, here's the reconstruction of what was happening. At about 1.4 million years, the porphyry was forming at depth. And at the same time, we had this dome present, perhaps a couple hundred meters higher elevation than present. And at that stage, coming off the top of that brine was a vapor. The vapor probably discharged because some of that vapor would have condensed into cold groundwaters, and the vapor would have flowed off along the unconformity, leaching the rock along the plane of the Lepanto fault. Of course, that alteration was barren. As we can see here in the residual quartz, but barren at this stage, that vapor was coupled to the potassic alteration stage. Subsequently, at about 1.35 million years, dating by Antonio Ripas, the first dated porphyry high sulfidation deposit in the world, demonstrating that they were linked not only in space, but also in time. That chlorite white mica fluid ascended over the porphyry and rose into the lithocap and deposited the enargite. We can see the enargite cement to the brecciated residual quartz, and that was a stage of copper and gold introduction. So that's sort of what we understand about this system. And that's the background. Now let's go in to discuss something about discoveries despite dogma of deposits in the epithermal environment. Many deposits have been discovered after several companies have been exploring in an area. Why? And the other question is, some deposits were discovered by the first company exploring in an area. How did they do it? Very simple questions. Of course, every discovery will have a different story involved, but I'll take a look now at a few examples that I'm familiar with. First of all, back to Yanacocha, the world's largest enargite gold deposit, but of course the enargite has almost all been oxidized, supergene oxidized, relatively easy to process. In the 1980s and through the early 1990s, all of the known gold deposits in the district outcropped at about 0.5 gram gold or higher. And so that was the thinking, or we now know the dogma, of Yanacocha at that time. And with residual quartz hosting the gold, with quartz alunite halos, essentially all of this alteration mineralization style was outcropping. Well, subsequently, Tony Longo was exploring in the area of the Chilean dome that we looked at earlier, and he came across an area of barren alteration of what's called granular silica. We now know the granular silica is actually supergene oxidized quartz pyrite alunite, the type of alteration that occurs on the margins of residual quartz that is the main host to high sulfidation gold and copper. And, oops, sorry about that. And here we see barren silica granular 2, barren silica granular 3, even though there was gold at depth, but didn't know that before it was drilled. And Tony argued with the company, should drill test that? And the response was, all of the deposits outcrop. So why are we going to drill a barren alteration? Well, finally, Tony got the drill holes, and the rest, as they say, is history. Beneath this barren granular quartz, which is the supergene oxidized quartz alunite pyrite alteration, was tremendously high-grade discovery of Chilean, 120 tons of gold at least, at an average grade of 5 grams. Here we see 60, 80 grams of gold at 15 grams per ton. So a great discovery, essentially blind in that area. And if they hadn't tested this barren alteration, it may still be undiscovered. Well, the reason that I briefly reviewed that is because it's important for this next discovery story. The discovery of Kimsacocha in Ecuador, now known as Loma Larga. These presentations, these slides on the I'm Gold website. And long story, in the 1970s, the British Geological Survey was exploring for copper in the area. They collected many samples, but they didn't analyze for gold. Well, in 1991, the French uranium exploration company got those samples, analyzing them for gold, and they defined a gold anomaly here at about 4,000 meters in southern Ecuador. They drilled a bit, but being a uranium company, they didn't really understand what they were doing. So after a few years, they joint ventured with Newmont and TVX. Newmont came in and drilled 82 holes, average depth 93 meters. Why? Because at that time, of course, all of the gold deposits at Yanacocha outcropped at the surface, and they were calling this area Yanacocha Norte, outcropping residual quartz alunite. They were looking for essentially outcropping supergene oxidized heap leachable deposits. Well, after 82 holes, they left, but then subsequent IM Gold joint ventured with Kojima, and IM Gold started drilling end of 2002, average depth 300 meters, and a year and a half later, 18 months later, 40th hole, they made the discovery, and within a year or so, they had a good resource. Well, let's just take a look at that. Here is the rationale for why the initial geologists were drilling shallow holes, because at Yanacocha, all of the gold deposits were outcropping. But however, I should say that Richard Spencer, the manager at IM Gold, was a structural geologist, and he was attracted by this 2 meters of 83 grams per ton in the Newmont drilling, the best intersection. And he thought, aha, that means that there must be a strong structural control of very high grades, narrow but high grades. So this is a geologic map, Newmont's geologic map in the area. We see this 4-kilometer cauldron here, a series of andesite flows away from that cauldron, subsequent intrusion of dacite domes, cutting through this early diatreme breccia in through here. And we're going to overlay then the alteration. And in this case, the Newmont alteration map showed residual quartz in blue and quartz alunite in sort of purple. And this is the area that Newmont largely tested, although they also drilled somewhat along these structures, but to shallow depth in the north along quartz alunite altered structures. This area here shows the eventual discovery, blind discovery of Kimsacocha. Well, of course, Newmont was interested because this was classic alteration and it was a large district, about 6 kilometers north-south. There's also were porphyry copper fragments in the diatreme breccia, so another part of the story. But they were drilling rather shallow holes. Subsequently, IAMGOLD came, and this is one of their really nice sections. It shows not only 1, but 2 lithocaps, residual quartz horizons, and those lithocaps were developed along permeable lapilli tuffs, whereas the andesite lava flows were impermeable. So 2 stacked lithocaps. And this doesn't show any feeder zone, so that tells us there must be a feeder zone somewhere off this section. Here it shows this lower lithocap. You can see this is basically a lapilli pumice tuff, unwelded tuff horizon. Well, this shows a discovery section, and it shows that the 40th hole by IAMGOLD drilling 101 meters of 9.5 grams. The highest grades were in the feeder zone. Lower grades that they'd been intersecting previously were out in the lithocap. And at 150 meters, 2 grams, 3 grams is simply too low grade. They really needed the high grade in the feeder zone to make this economically viable. By contrast, the shallow lithocap was basically barren. And that was the lithocap that Newmont had been originally testing with their Yanacocha model. Well, not only stacked lithocaps, but the upper lithocap was barren. So very simply, this shows a long section with mineralization basically confined to about 3,600 meter elevation level, 150 meters deep. The lesson here is drill sufficiently deep and look for the feeder zone, test the feeder zone. Okay, we started at Yanacocha here in the north. We moved a little bit to the north into Ecuador. Now let's come back to northern Peru, where over about 16 years, 3,000 tons of gold were discovered in lithocap-hosted deposits. Northern Peru. First Yanacocha in mid-80s, followed by Parina in 1996. The Alta Chicama was discovered in the year 2000, but it was after 1996. And I should say that the major companies were not looking in southern Peru because southern Peru was a very well-known silver district. And so these major gold companies said, well, why should we be looking for gold in a silver district? However, a Peruvian national company, they weren't too worried about that. And after 1996, the Argentine company sent their chief geologist down to southern Peru to look for this style of deposit. And they initially found a small example in 1997 that led to a large example discovery in 2000. And that started a gold rush back to southern Peru that then led to the definition discovery of Chuquipaca. And I'll review those examples now. And so it wasn't until 2002 that we started finding multi-million ounce deposits in southern Peru, now greater than 300 tons gold having been defined in these 5 southern Peruvian departments. Well, this was a view over the Tucari deposit in the Argentinian district. We can see the deposit outcropping here above 5,000 meters elevation. And this presentation in 2004 was recent discovery of a new ore type in an abandoned lead zinc silver vein mining district. In fact, that lead zinc silver vein district was intermediate sulfidation veins. And here we see that was Cacachara, intermediate sulfidation veins, small, that had been mined in the 1980s. And that's what Agrantani came back to look at. And they eventually discovered about 3 kilometers away the small Santa Rosa high sulfidation style deposit, about 0.4 million ounces of gold. But as they started working in this area, proving up that deposit, they carried out district exploration. And of course, that then led to definition of the deposit at Tucari, the alteration halo, and the larger deposit, about 2 million ounces at Tucari, about 25 kilometers to the northwest of Santa Rosa. And that was all because they said, well, why can't there be this style of deposit in a district with silver-based metal veins? We now, of course, know those are intermediate sulfidation veins. They fit our general occurrence model. So this is Tucari, looking to the north. Dacite intrusion hosted residual quartz alunite halo around here. The gold's in oxide. And let's look at a cross-section through the deposit. Now, this shows the Barossa andesites in the area, which largely are not themselves mineralized. They might be altered, but they're not mineralized. However, mapping by Wolfgang Morsche demonstrated that in the district, there's a very important series of dacite dome intrusions. And it's those dacite domes that brought with the hydrothermal systems and also the metals. And here, we'll fade that over. We see that the dacite domes are the focus of the alteration, the residual quartz, granular to vuggy, and also the gold mineralization, greater than a quarter gram per ton gold in this area, average grade about 1.6 grams per ton, and with a halo of quartz alunite here in orange. So absolutely classic deposit, outcropping at the surface, and had been passed by because this was a silver district or a silver region prior to its discovery. So first discovery of Santa Rosa, then leading to discovery of Tucari, it reawakened interest in the region, and that led to Goldfields coming in and other companies. Goldfields came in then and joint ventured with Buenaventura, and they started exploring in this area to the northwest, about 70 kilometers, defining the Chuquipaca district. And Goldfields found a nice dacite dome, altered to quartz alunite, some residual quartz along structures. They collected surface samples, largely less than a half a gram, a few a little bit higher. And they put in 12 holes, nothing really very exciting. And at that stage, they decided to leave this because it looked like this was a barren lithocap, not a very well mineralized lithocap. And their joint venture partner, Buenaventura, had some interest because they were a base metal miner and they were interested in the sedimentary sequence in this area, the potential of these sediments, carbonates particularly, to host carbonate replacement deposits. And they saw, of course, this gossan here. So Buenaventura started drilling, and they drilled 5 holes. They found no zinc, no gold either. But on the 6th and last hole of their exploration, they were drilling this area of gossan. They discovered intermediate sulfidation, mineralization. What was that? I had to write it down. 60 meters of 3 grams gold and 0.5% copper. Still no zinc. And I've shown that this is actually a pseudogossan because it's not oxidation of sulfides. It was actually oxidation of iron carbonates, anchorite, siderite, that caused this gossanous material. Classic typical association in intermediate sulfidation situations of iron carbonates. So the discovery by Buenaventura in 2008, Goldfields then backed in and drilled out a deposit, a total of about 230 tons of gold equivalent in this deposit, subsequently sold, their share sold on to Buenaventura, who's since renamed the deposit, the Cañuerí deposit, San Gabriel. And this deposit, very interesting, plunging steeply. And the reason it's plunging is it's following a diatreme, brachiated diatreme, multiple diatremes in this area with higher grades at depth, located 2 to 3 kilometers from this sterile quartz alunite altered dome system. So this is an example, even if the quartz alunite, residual quartz altered center lithocap is barren, look for other potential in the same district. So not only thinking laterally, but in this case, looking figuratively laterally as well. And the last example here of a discovery, well, actually 2 examples. We'll look to further south in Chile, the Lepanto district, a Triassic sediment hosted residual quartz zone, but the upper third or so hosted by tertiary volcanic rocks, a series of high sulfidation deposits. But over the top of those deposits is over the top of Coipa Norte at least, is a very nice steam heated alteration cap over the hypogene quartz alunite alteration. And that steam heated blanket sitting right over the top is basically barren. So on that basis, Placer Dome, well, originally Codelco started to assess this area of steam heated alteration to the north, about 4 kilometers. And Placer Dome then also started testing this area, about a dozen holes put in this area of steam heated alteration. And again, go back to Antonio Ribas's presentation on the 4th of May to learn more details about how that forms. Well, here we have the steam heated alteration of Peru South, underlain by a flat lying horizon of chalcedony formed at the paleo groundwater table. This area, 12 holes, unsuccessful, but fortunately, Placer Dome continued their exploration in the area, and they moved, they were continuing geological, geophysical, geochemical exploration, moved to the Peru North area here about 2 kilometers away, and beneath about a 30-meter blanket of steam heated alteration, shown in blue here, discovered the Peru silver gold deposit. And that was about 90 tons gold equivalent discovery in the early 2000s. A very nice blind discovery, satellite ore body. It was very important for the company at that time. Codelco was very happy as well. They were land owners. They had a share in that discovery. And importantly, though, is that other people learned from that discovery. And that led directly to the discovery of the Salares Norte deposit in about 50 kilometers to the northeast. And this discovery by Goldfields, I should say this presentation by Nate Brewer, Chico Azevedo, and others with Goldfields. Nate and Chico gave me permission to use their slides for this. Here we're looking at Salares Norte. Goldfields started considering this district, or this region. They knew that the Maricugna region was very prolific, about 2,000 tons of gold, largely associated with gold porphyry systems, but also at La Coipa, a high sulfidation deposit. Esperanza was also a associated deposit, but very little effective exploration done here further to the north. Well, they started exploring this area of extensive steam-heated alteration, barren steam-heated alteration in the north, but knowing about the discovery of the Peru deposit nearby La Coipa. So that was a very important part of their exploration model. They had identified 4 deposits, 4 prospects, I should say, and because of its remoteness and elevation, Salares Norte was the last deposit that they started looking at in this late Miocene cross-cutting volcanic arc, cross-cutting the early to mid-Miocene Maricunga district here further to the south. Well, here this shows an aster image of the alteration in the area. Alunite and kaolinite in orange and yellow alteration here draped over this dacite dome, and blue showing silica, chalcedony deposition. So that was certainly one of the things that led them to this area, targeting the steam-heated alteration very well developed on the flanks of this dacite dome. And right on the margin of the dacite dome, also a diatreme. Everything basically coming together for gold fields, except that after collecting several hundred soil samples or talus fine samples, essentially all of those samples were barren, less than 24 ppb gold, except one sample at about 0.6 grams, shown right here near this diatreme breccia, which in fact called the breccia principal, but it's a polymicted phreatomagmatic breccia with wispy juvenile class. One sample there running 0.6 also should say that all the rock chips in the area were barren, less than 35 ppb gold, and yet with anomalies of the epithermal suite, arsenic, antimony, lead, bismuth, and mercury. Well, set up a drill rig, first hole, lost it, difficult drilling conditions, RC hole, put a second RC hole in, and that hole was basically a discovery hole, 96 meters of 1/2 grams from 190 meters depth, drill depth. Brought in a core rig and went from strength to strength. Now, here, very, very proper plotting of sections with the mineralogy. I've sort of summarized them as hypogene advanced argillic alteration. We can see the quartz alunite alteration largely hosted by this diatreme outlined in purple, extending to the surface. And then we also have the this light blue steam heated alteration in through here, shallow level, down to the paleogroundwater table alteration. That alteration basically barren, unmineralized. And then everything again was overprinted by another style, again, going back to Antonio Ribas's presentation, another style of advanced argillic alteration, that being due to supergene oxidation. And here, the supergene oxidation even overprinted the early hypogene mineralization with its pyrite and possibly some enargite. So complicated, 3 styles of alteration, which you can read up on going back to Antonio Ribas's lecture or listening to Antonio's lecture. But importantly, the mineralization basically had a very sharp top, basically the top of the paleo groundwater table. And yet that didn't bother goldfields, coming across only barren steam-heated alteration. They realized that if there was a focus like this, phreatomagmatic diatreme, that could potentially have focused the deep system to be subsequently mineralized at depth, and led to the discovery holes with locally some very high-grade gold, up to 3 kilogram per ton gold mineralization developed locally, related to some creamy silica depositing, sealing these this brecciated diatreme. So a very nice resource. The last I looked at in 2018, 23 million tons of 5 grams gold, 66 grams silver at 95% indicated. A great discovery, and basically all because they knew what they were looking at. They weren't really coming in with any dogma. They were looking at what the rocks were telling them. So in summary, of course, the early we discussed the early vapors, how those generate advanced geologic alteration. We looked at how those vapors are related to the deeper intrusions, the part of the lithocap caps over the tops of porphyry systems, realizing that at the time of formation, the lithocaps themselves may be barren, and possibly some of those lithocaps can then be mineralized related to the porphyry copper mineralization. We looked at several examples, some of which had the discovery company was second, third, fourth company, and how maybe some of the early companies had come with too much of a dogma, a model that they were working on. So, bottom line, there are no magic bullets in exploration. It's only good geology being applied by good geologists. Don't force evidence, geological evidence in some type of model, theoretical model. If you've got a local occurrence model, that's fine to help guide you, but not into any theoretical model, particularly something's coming from another country. But then use your good geology observations to have lateral thinking, not only literal, but also figuratively, and help that to focus your evidence into developing targets that then can be tested by deep drilling. And with that, I think I should cut. I've been talking long enough. I will turn this back to the panelists, the organizers. Thank you for your attention. Monica, are you going to, or Nicolas?
Yes, Jeffrey, we're here.
Okay.
Thank you for your presentation again. Now we'll have 1 or 2 minutes in order for people to make their questions.
Yeah. Let's see. Yeah, I saw a few questions coming in there. Talking, but
yes, we're organizing them in a certain order in order to.
Yeah, no problem.
Okay,
yeah.
Great.
I'm sure there are some general questions, also maybe some specific questions. If there are specific questions, I can try to go back to and screen share my PowerPoint. I can go down here and for any.
Hi, Jeffrey.
Yes.
Maybe you can start answering the first question. Is from Milton Gonzaga. He asked, what is the difference between polymetallic and intermediate sulfidation veins?
Yeah. Well, terminology. Polymetallic is simply meaning multiple metals, of course, and it usually includes silver, maybe gold, copper, lead, zinc. And as soon as we start putting the name intermediate sulfidation on, we start thinking of, those theoretical models. So polymetallic is very descriptive, and all intermediate sulfidation veins probably are polymetallic, but maybe not all polymetallic veins are intermediate sulfidation. So stick with the descriptions rather than necessarily worrying about any names. And I introduced the terms low and high sulfidation in 1987, and then after David John's work in Nevada, we sort of added the term intermediate sulfidation for the types of veins in volcanic arcs to distinguish them from low sulfidation in extensional zones. But I try to get away from those names as much as possible and just rely on descriptions. Very important point.
Eric Espinosa asks, between the hypersaline fluid and the steam, which are X-dissolved, which one carries more metals in volume?
Yeah, well, that's a good point. Basically, where do the metals go? And some people probably have been reading about analyses of these vapor-rich inclusions using laser ablation ICP-M mass spectrometry. And in about 1999, it was discovered that these vapor-rich inclusions had a lot of copper in them, possibly even more than the hypersaline inclusions. And so then people started thinking, oh, you know, the vapor is transporting all of the metals, the copper and the gold. Subsequently, various people, Andres Otate, along with his student, Linda Luschbaumer, and Zoltan Zachas, and others, they've been looking and they realized that, unfortunately, this is one of nature's artifacts because there's a lot of H2S in the vapor, and copper diffuses, after trapping, copper diffuses into the vapor to result in these high but artificial copper values. So it looks, certainly copper, well, certainly gold can fractionate into high pressure, high temperature vapors. There's still a lot of work being done on it. But the bottom line is perhaps it's not so important if in fact, as I argue, or I should say we argue, that most of the copper is being introduced by this unseparated fluid that basically, I'll go back there, that basically has an intermediate salinity of 5 or 10 weight percent. So perhaps, at least in the epithermal environment, we're not so worried about whether it's the brine or the vapor that had the metals, because this is the later stage. So there's still a lot of work being done, but anybody who wishes to follow this up, read some papers by Luschbaumer and Otate in economic geology, and then also another one by Zoltan Zachas on the behavior of the metals between these various fluids. But I don't really worry too much about it. I really try to make observations of the alteration mineralogy. Yeah, good point. Still evolving. We're still learning. Next.
Question from Jose Añasco. Why some deposits have porphyry mineralization at deep with barren lithocaps and other ones are mineralized at deep but also in the lithocap? What does it depend on?
Yeah, well, it may depend on simple geology. For example, here, there's a porphyry in this model. There's a porphyry being shown with the chlorite white mica fluid rising into the lithocap, maybe bringing metals to the lithocap. But remember what I said, if that fluid does not, for whatever reason, does not rise to the level, you're left with a mineralized porphyry, but a barren lithocap. And maybe it's because that, I think very simply, that white mica fluid could not reach the level of the lithocap. And imagine where instead of relatively flat-lying topography, we have a larger vertical relief. And so the lithocap has developed maybe over 1 kilometer, 1.5 kilometers above the porphyry, such that the later mineralizing liquid cannot get to the lithocap. And maybe it flows off laterally to the marginal veins. And so it's almost a physically leaving this barren, this lithocap barren, instead of rising to that level. So I often tell geologists that epithermal geologists, to think like paleohydrologists. What was the original hydrology of our system? Was it high relief or relatively low relief? At high relief, then we're going to have strong hydraulic gradients in the epithermal environment. And so we have to think laterally as well as vertically. So a very good point. And I can't answer always why, but in part, simple physically not being able to get the ore fluid up to the vapor-formed advanced argillic alteration. Next.
Okay, thank you. Juan Arbea asks, how is dome formed and what is its importance in the generation of epithermal deposit?
Sorry, how do domes form?
Domes.
Yeah, domes. Well, as Silito showed here, there is commonly dome events. Domes are simply a near surface intrusion to extrusion equivalent of the deep intrusive system. And for example, let's see, we see the work by Pete Dunkley here. He suggests that probably there was no more than about a 200 meter more volcanic edifice, and probably based on dome features, flow banding, etc. This probably was a dome over the top of the porphyry. And this simply was part of the intrusive extrusive system. Now, if you have a dome present here, like also was present at Chuquipaca, sorry, not Chuquipaca, at Yanacocha, senior moment here, the dome-related deposit at Yanacocha, you know, that may, in case of a dome, that dome margin may be serving then as a vertical feeder, and then the fluids can intersect some fault or laterally a permeable lithologic horizon. So domes are just part of the volcanic system. They don't have to be there, but as you could see, for example, at Chuquipaca, these are quite common. They're also present at Tucari, so we should certainly look at them when they are present. At least they're telling us where the proximal part of our intrusion-centered system is, because they tend to be proximal. The domes don't really occur out on the margins so much. I'm not sure if I answered that well, but that's, yeah. Okay, next question.
David Arribas Plata asks, the size of the lithocap is the reflect of the potential size of the porphyry on depth that generated?
Yeah, size of lithocap, is it related to the size of the porphyry of the intrusive system? Well, I would have to say not necessarily, but it is possible. If I saw a small area, if I went to a prospect and there was just a little bit of minor advanced argillic alteration, hypogene, crystalline alunite, as Antonio Rivas discussed, crystalline alunite associated with quartz, maybe some dicite, diaspore, etc. But just minor zones along fractures. And then there was another prospect 20 kilometers away with 5 square kilometers of this same style of alteration. I know where I'd focus first, the area of more extensive alteration. But I could imagine situations where simply a lot of the vapor rose along fractures and maybe the wall rocks were not permeable. So the wall rocks did not host the advanced argillic alteration to the same extent. Like at Summitville, the first high sulfidation deposit, well described, there the residual quartz is only narrow along fractures and does not extend into the dome itself because there was no permeable horizon within the dome. So keep the original lithology and permeability of the rocks in mind when you're interpreting the style of alteration. But you know, there may be some relationship between size of alteration and underlying system, but there may be exceptions to the rule. So be careful about generalizing too much. Next.
Okay,
Monica?
thanks, Jeffrey. The next
Yeah.
question is, what were the most common mistakes made by first exploration companies to not find deposit in the first instance?
I'm sorry, the first half of the question, what was the?
What were the most common, yes, what were the most common mistakes made by first exploration companies to not find deposit in the first instance?
Okay, mistakes. Well, I guess we could call it a mistake, because if you have the property and explore there or even drill and then walk away, and later a company came and found a deposit, we could probably call it a mistake. You know, I wasn't involved at the early stages, but as I said, originally Kimsacocha, now Loma Larga, was known as Yanacocha Norte. So they were squeezing that Ecuadorian prospect into the Yanacocha model, where all gold deposits outcropped at the surface, rather than thinking maybe we should be drilling deeper and looking for structure-controlled high grade, as I'm Gold subsequently did when they recognized that these, you know, this was a somewhat different style of structural control and lithologic control. So really look at the geology, look at the lithology, alteration, etc., and interpret what that was telling you, rather than necessarily lean too heavily on on models. Of course, you know, we all base our work on our experience, and we try to build on the experience. And sometimes we build on it, but we have to not try to apply our experience completely to interpreting one deposit. We have to really interpret it on the basis of the geology of that one prospect. So I'm sure that there are many causes, reasons. So just keep your eyes open and interpret what you see.
Okay, fine. The next question is, let me see. Is there any relationship between the cordilleran type deposits and the high sulfidation phase in the porphyry system?
Okay, relationship between cordilleran and high sulfidation deposits. Cerro de Pasco has been called cordilleran, and it's of course carbonate replacement, galena sphalerite silver deposit, but it's sitting right next to a dome diatreme complex cut by advanced argillically altered veins and structures hosting enargite and gold mineralization. And the original discovery was made in the 1800s. The original mining was of the enargite and gold. And it was the Cerro de Pasco was discovered, the replacement deposits, because they were mining underground the enargite gold veins, and they then encountered the marginal carbonate rocks with lead, zinc, silver. And for a variety of reasons, you know, even then they didn't like the enargite as much as just sphalerite and galena, and the higher value of the silver in those days. So they pursued it. So coming back to the question, is there a similarity? Well, you know how in Espanol, I don't know, what is it called? You know, the blind men filling the elephant. Nicolas, is there a term in Espanol for blind men filling the elephant? That story?
Yes.
Yeah. In Espanol, what is it?
Sorry, what?
What is the story in Espanol? Blind men feeling the elephant.
Blind man feeling. I don't get that.
Okay, well then the story, the children's story, is not easily translated perhaps to Spanish. But you know, There are three blind men, and they cannot see, but they're feeling an elephant. And one feels the trunk. They say, "Oh, this elephant must be big and thick." And another one is feeling the ears. "Oh, no, the elephant is thin and floppy." And another one is feeling the nose. "Oh, no, long and narrow. That's a deposition elephant." So it depends on our experiences. And Luis Pompote and I can have a long discussion, very enjoyable discussion and argument if it's over a good bottle of wine, in the use of the terminology. So they're coming at it from one direction, I come at it from another direction, but I would say that fundamentally, these are intrusion-centered, magmatic intrusion-centered deposits. The carbonate replacement deposits, the Cordilleran deposits, they are intrusion-centered, and they may be, like at Coquihirca with Marcapunta, they may be enargite gold-centered lithocap-hosted systems. So really, it's a problem in terminology. If we describe what we're talking about, we're going to be talking about the same things, the same elephant, just using different names. That would be my argument. Okay?
Okay, fine. The next is,
Yeah.
what's the time scale for the formation of epithermals compared to the associated porphyry system?
Same time scales, because they're all forming in the same environment. And overall, there's been various dating done for the last 4 decades or more, and some suggestions that porphyries form over 1 to several million years. Yes, porphyry districts, but not individual porphyry pulses and events, and also not individual epithermal deposits. They're probably forming over tens of thousands of years, and possibly even less, the actual event of metal deposition, even very short periods of time. But where we get evidence for long periods of life of the alteration is probably due to overprinting of multiple intrusions that may be causing the porphyry to become a larger deposit, but there are multiple events. So porphyry and epithermal are probably forming over the length of just thousands of years. Some people suggest even much less than that, the actual metal event. But then the overall districts of several hundred thousands of years to even 1 million years. So it, again, depends on the scale you're looking at, but very short. As Marco Iannotti said, when porphyry deposits are forming, it's like a wild Saturday night party. All kinds of things were breaking loose in a very short period of time. Next.
Okay, there's someone asking, can you elaborate a little bit more on what you call lateral thinking?
Oh, lateral thinking. Well, as I suggested, lateral thinking, the more, the older we get, the more gray hair, the more experience, sometimes the better we are at lateral thinking, because we're saying, well, what about if it's a little bit like that and a little bit like that deposit, things that we've seen. So we're basing this lateral thinking on experience. And I know, for the students here or young geologists, experience means time. It means time in the field. So basically all I encourage is for people to take as much opportunity to get into the field, to work in the field, mapping, to look at different ore deposits and whatnot, to help develop this experience that will then allow your geological training to then start being applied and say, well, what if? I know that this is what my geological training is telling me, but then how can I extrapolate that? How can I think laterally? But also, of course, literal thinking, because in the epithermal environment, once we get to within the upper 500 meters or so of the surface, there's very strong hydraulic gradients caused by topography. So we have to be thinking like a paleohydrologist. Where are the fluids going to be going as they follow hydraulic gradients? And if there's lateral flow because of topography, then that is perhaps where I want to follow. So what is the mapping results indicating? Can we see any asymmetric zoning in the alteration mineralogy, etc., that's suggesting that there's some asymmetry or there's some lateral flow, and maybe the deposit is at some point distal or more proximal along that lateral flow path. A little bit, again, going back to Chicopaca and Cañuery, now San Gabriel, that intermediate sulfidation system mineralized a diatreme, i.e. a source of permeability that was about 2.5 kilometers away from that dome-centered part of the system. And although the data are not public, let's just say that that deposit and that dome itself, the relatively barren dome, all formed in a very, very short period of time. So it was all active at the same time. So that would be a very good example of lateral thinking. Looking across and seeing, oh, there's that Gaussian 2.5 kilometers away, and there is also 1.1 gram gold anomaly there. Perhaps even though it's not associated with this dome, maybe we should be looking at how that might fit into the whole picture. Okay. Not sure how much.
Next question.
Yeah.
Once a lithocap has been identified, will it be coherent to rely on magnetic low anomalies in the alteration zone to choose where to drill?
Sorry, I missed that. Did you say magnetic anomalies?
Yes, I'll repeat the question. Once a lithocap has been identified, will it be coherent to rely on magnetic low anomalies in the alteration zone to choose where to drill?
Well, yeah, okay, magnetic low. Of course, many fresh rocks have variable magnetic signatures, magnetic high signatures. And then once those rocks are being altered, those signatures, whether it's a broad zone of alteration or possibly narrow along a structure, the magnetic signature is being destroyed. And so we can see magnetic lows associated with alteration. Sometimes in lithocaps, there's so much alteration that it's completely destroyed. But then let's think a little bit deeper, depending on if we're only looking for the lithocap, think a little bit deeper. If there's an intrusive center, and if it's magnetite-rich potassic alteration, we might see a magnetic anomaly associated with a deep porphyry center. On the other hand, if there's a lithocap there, it might be too deep to see, or it might have been destroyed by white mica alteration. The magnetite might have been destroyed. But magnetics is not so useful in the lithocap itself. However, if we want to use geophysics, what might be useful? Here we have a lot of leached rock, residual quartz. Residual quartz has a very high resistivity of at least 1,000, sometimes 10,000 ohm meters resistivity, in contrast to, say, kaolinite alteration that might be forming kaolinite dickite forming on the margins, which might have only hundreds of ohm meter resistivity or less. So possibly a technique like CSAMT or even EM, you could fly EM over an area and determine the resistivity to a few hundred meters depth and get an idea where the highest resistivities are. Now, fresh rock will have resistivity of maybe 1,000, 2,000 ohm meters. So the lithocap might only be that, but if you see 10,000 ohm meters, that's probably certainly residual quartz. But before I do that, definitely walk over the area, map it, get a good idea of what the distribution of the alteration is, the style of alteration, and where the structures are going. Start with mapping, and once you see what the rocks and the alteration are, then decide what's the best geophysical technique to possibly bring in. recognizing that geophysical techniques are usually expensive, a lot more expensive than employing geologists to map. Okay.
Okay, fine. The next one is, may deep in place porphyry systems produce world-class epithermal deposits like Yanacocha?
Sorry, the very first part of the question, world-class epithermal, do we need world-class porphyries or what?
Yes. May deep in place porphyry systems produce world-class epithermal deposits like Yanacocha?
Yeah. Well, that's another question that's often discussed. If you have, if you have a very large epithermal deposit, gold, copper, of course, the copper sometimes is supergene oxidized and removed. But if you have a very large epithermal deposit, does that mean you're going to have a large porphyry at depth? Well, one possibility is that all the metal leaks through to the epithermal. So perhaps it's only a subgrade or a low-grade porphyry at depth. But then you look at an example like Lepanto, 4 million ounces gold, 1 million tons of copper, and at depth, the genetically related far southeast porphyry has at least 5 million tons of copper and 20 million ounces of gold, roughly the same ratio. And so that's a good example. Now, I'm sure that someplace beneath Yanacocha, there is at least one, if not several, multiple porphyry systems. One has been drilled at Kuffertal with some 0.4, up to 0.4 grams gold, 0.4% copper, but it's not been drilled out. I only know of about 5 holes been drilled there, but perhaps there's been other holes drilled. There have also been some deep drill holes there that haven't been very successful, but almost certainly because they haven't hit the porphyry center. So, but having said that, you know, there are a lot of barren lithocaps that are still preserved, sitting on the margins of world-class porphyries. And in other cases, the lithocap has been completely eroded through, you know, in some deeper erosion areas like Southwest United States and the laramide rocks. So all possibilities there are, you know, I think we can see examples of all possibilities of world-class epithermal with underlying world-class porphyries with no epithermal mineralization, but large lithocaps, or epithermal completely eroded away as well. You know, there's very variety of possibilities, I think.
Okay, thanks, Jeffrey. The next one says, is there any mineral that registers the geochemical signals of the epithermal environment which is not affected by weathering and transport?
Gold's pretty good. You know, certainly there is a residue of arsenic. As I pointed out, there was arsenic, antimony, bismuth, even mercury in the supergene environment at Salares Norte. You know, may not be high, extremely high, but you know, and although we can generalize, the most important thing is to decide locally what is geochemically anomalous. What are the, if possible, go to a prospect, another prospect, or even an old mine dump somewhere in the district, and find out what elements are anomalous, and even what are the thresholds of anomaly. And the reason that I don't generalize about geochemical anomalies is because there are a lot of variabilities in the metals that are anomalous, as well as the thresholds. If we, you know, completely different environment, low sulfidation, if we go to Halmaheras, the porphyry deposit there, 1 ounce, you know, 40 grams per ton gold, the arsenic anomaly there is 20 ppm arsenic. That's a high anomaly. and even 10 ppm is anomalous there. Whereas a lot of places, other places, you know, if we even see 100, 200 ppm arsenic anomalies, we would not really be very excited. So it really is important to know what are the levels of anomalies of the various elements that are anomalous, that are characteristic of a district. And we can go through, you know, a whole list of the epithermal anomalies, but also bismuth, tellurium or selenium, tellurium particularly, molybdenum, sometimes very anomalous, other times not anomalous at all in the epithermal environment. So do your orientation surveys in an area to find out what do you think, what should you be looking for, and what are the thresholds of interesting levels of anomaly. Okay.
Okay, thank you. The next one says, in low intermediate sulfidation systems, the boiling process plays a very important role in the precious metal precipitation. But what happens in high sulfidation systems? Have you seen boiling textures in high sulfidation systems?
Okay, well, that's a good question, but a very involved question. Boiling is important in low intermediate sulfidation systems. Was statement should be low and intermediate sulfidation. I have seen people with low/intermediate on some epithermal, but it's always one or the other. Again, the name isn't important. Don't worry about the name. But in these vein systems, yes, typically we see evidence. A variety of evidence, whether it's adularia, which is generated in boiling systems, or carbonates, sometimes bladed textures, etc., for boiling conditions. And we could have a whole lecture on that, of course, going back to the geothermal analogs and discuss why that's so. But also, it's important to consider how important boiling might be in the enargite gold deposits. I have not seen quote unquote boiling textures in terms of adularia or carbonates in lithocap hosted deposits. But that's probably because there's no component left in the rock to form adularia or even a carbonate. Because the gold that's deposited in lithocaps, the gold was deposited by more neutral pH solutions, 4 to 5. It was like a muscovite stable solution. We can see in the direct shipping ore at El Indio, there, the alteration halos are white mica, not alunite or aluminosilicate. But what we do see associated with gold that argues for boiling to be important is that we see I just mentioned briefly, the laminated colloidal silica at Salares Norte, the creamy quartz. That's indicating that amorphous silica was saturated. And almost the only way to get to amorphous silica saturation at high temperatures, 200, 250 degrees, a few hundred meters depth, is by boiling and vapor loss. I've got a diagram. I don't think it's necessary to bring up the diagram. Let's just say that colloidal silica, not, you know, this is different from, careful, this is different from colloidal silica in acid crater lakes. That's something else. And that's where you also get evaporation. So that's contributing to colloidal silica saturation there. But in the fractures of high grade gold, you get this colloidal silica, which is formed because the vapor was lost from boiling. You saturate with amorphous silica, and the two go hand in hand. Creamy quartz. The first place I saw it was at El Indio, creamy silica in the direct shipping ores. And anytime you see tens or hundreds of ppm gold in this environment, commonly you'll see the creamy silica. Okay, now, even more complicated perhaps, or continuing on, at Lepanto, when we look at the fluid inclusions in the enargite itself, Dan Mancano showed that the fluid inclusions indicated a very simple dilution trend of higher salinity, higher temperatures, close to the porphyry, lower salinity, lower temperatures, further away from the porphyry, simple dilution trend towards a steam-heated diluent, suggesting that at least the enargite was being deposited by dilution characteristics. And, this was not a discussion about the mechanics of deposition of enargite and gold in this environment. Otherwise, we could bring more examples. But it does appear as though a lot of the gold does deposit after the enargite stage. Usually gold follows copper. So we still don't really understand completely the depositional mechanisms of copper and gold in high sulfidation deposits. But dilution is important, particularly in the lithocap and particularly with enargite. But I would argue that particularly high grades of gold, maybe not 1 or 2 grams gold, maybe 1, 2 grams, 3 grams gold could be deposited from dilution. But if we get tens, hundreds of grams of gold, probably boiling was involved, particularly if you see the creamy silica, colloidal silica laminations. Let me pull this down here to that one quick example I showed, which the PDFs don't have this because this is a, Nate and Chico lent this to me and I wouldn't want to use their commercially confidential or put it out in a PDF for everybody, but they did say I could use it in the presentation. You can see in this breccia, this is about this is 1.5 kilogram per ton gold zone, brecciated material, and the gold is associated with this finely laminated colloidal silica, this creamy chalcedony that we'd like to call it. There's visible gold right through here. Cannot see it now. So that's a long-winded, roundabout discussion of this topic. We don't have the final answer yet, but those are some observations. Sorry to make it so long. Okay, next question.
Okay, Jeffrey, thank you. I wanted to ask you something first. How many more questions can we have?
Nicholas, it's up to you. I guess as long as you and I are still, maybe everybody else turns off, but as long as you and I are here, we can keep talking about questions. I don't have any, I think you also have another presentation later today at Bogota, right?
No, we don't have any more presentations today.
Okay, but it's up to you when you think that the questions are decreasing, etc.
Okay.
Totally up to you.
Yes. So we'll have some final questions. One of them is, arsenic is the best pathfinder of gold. What is the relationship between gold occurrence and arsenic?
Well, I would not say that arsenic is the best pathfinder. It's a pathfinder in some cases, as I discussed previously. It's common even in supergene oxidation of enargite or tennantite tetrahedrite, enargite leucine or tennantite tetrahedrite. It commonly remains as scordite even after the copper has been leached from the system. But there are some cases where it's only hundreds of ppm rather than thousands. The reason that arsenic is there is, of course, because of the original enargite, leucinite, tennantite tetrahedrite. But again, we have to look at other all of the other metals in a given district to decide what is really going to be the anomalous metal. Since scordite, arsenic oxides are stable, they commonly stay around the system after supergene oxidation. I don't know. Did I address that? What was the question exactly?
The exact question was whether the relationship between
Okay. Nicholas, you're cutting out on at least I can't hear you quite.
Can you hear me now?
Now I can, yes.
Okay, the question was, what is the relationship between gold and arsenic? I think he's asking for the genetic relationship.
Yeah, well, actually, I mentioned that, of course, enargite is very common, but another possibly reason for the question, and it is a good question, because at Yanacocha, much of the gold was associated with Arsenian pyrite. Arsenic-rich zones growing over pyrite. And the studies by Reich and Deditius have shown that where the pyrite is not oxidized, have shown that the gold is sitting with the Arsenian pyrite rims. Now, if you still have the Arsenian pyrite there, well, maybe that's where the gold is. Of course, if it's all been supergene oxidized, then you don't know if that in fact was the location of a lot of the gold. But again, when we see the gold at very high grades, then it's often with the colloidal silica, the laminated colloidal silica. So I would say that both enargite, but also the Arsenian pyrite would be the main reasons for arsenic and gold association. Okay, next question.
Okay, next is an interesting one. It says, what do you recommend to the young Colombian geologists to make a correct mapping in a country where the vegetation is very dense like ours?
Yeah, no, that's the reality, isn't it? That's why I like working at 4,000 to 5,000 meters in Peru and Chile and Argentina, because it's very dry and not much vegetation covering things. You go further north to Ecuador, then Colombia and other regions of the world, and that's the reality. Thick jungle, thick lateritic horizons, etc. Yeah, it's not easy. I've not worked up there very much, and possibly because I wasn't invited back because I didn't do a very good job in helping you out. But get as much geological information as you can. Look at the original rocks. And of course, if one area is very strongly altered and deeply weathered, then look outside where at least they're only weathered, not altered. And then sometimes you can see the fresh rock textures. What are you looking at? What are the host rocks, the lithologies? Are you looking at domes, etc.? So then at least you have that lithology information. So when you go into the areas that are more strongly altered and weathered, perhaps you have a better ability to see through that alteration and weathering to first figure out what the lithology was, and then second, what the alteration was. But one thing to note, if you have hypogene quartz alunite, or particularly residual quartz, no amount of weathering, no amount of tropical weathering is going to affect that. It's going to stay as cliff-forming advanced quartz alunite or residual quartz alteration. Yes, if you've got argillic, if you've got kaolinite, dicite, pyrite alteration, that's going to break down and erode, but the core of the system, the residual quartz and quartz alunite, is still going to be there. Okay?
Okay, that's great. The next one says, do you know about studies of epithermal mineralizations located in the Amazonian craton? What do you think about these processes, the formation processes, in comparison with Mesozoic types?
Yeah, I've only read about it, and another senior moment here. The name professor has published on some of these examples, very old examples, and I've never looked at them, so I don't know for sure. But what I've read in the papers, their alteration characteristics, for example, their stable isotope characteristics and whatnot, it looks like they have much of the same alteration features, geochemical features of the younger deposits. So yes, there certainly I've seen Paleoproterozoic 1.7 billion, 1.17 million year old deposits metamorphosed in Sweden and Finland. So there's really no reason why we can't have lithocaps, residual quartz with aluminosilicate halos, why they cannot be preserved back in time as long as that environment is preserved. And even if there is metamorphism and shearing, you're still going to see, perhaps you're going to see silmonite, cordierite, andalusite halos, but they were originally aluminosilicates like kaolite, dicite, porphyry. So again, lateral thinking, how might this is originally looked at if it wasn't metamorphosed? And the Enersand deposit in Sweden was first called a metamorphosed sandstone horizon. Well, it wasn't a sandstone horizon, sedimentary horizon. It was residual quartz that was then sheared out. And the silmonite, cordierite halos were original kaolite, dicite halos around that body. And it was sheared almost 10-to-1 aspect ratio. Hallberg has published some papers on that, shows the evidence for the shearing. So old rocks, even if they've been metamorphosed and or sheared, they should still preserve these. So think laterally, is it possible that this could have been an epithermal system rather than a orogenic, very old orogenic, which are also present, of course. Okay. Next.
Okay, next one says, high molybdenite contents in intermediate to low sulfidation epithermal gold veins could indicate shallow genetically related intrusions?
Sorry, high molybdenite? Was that the question?
Yeah, molybdenite.
Yeah. Well, again, if we consider extension-related bimodal magmatism-related epithermal environment, sometimes we call it low sulfidation, but that low sulfide containing gold-rich epithermal environment, some deposits, molybdenum is hardly anomalous, a few ppm. But then others like Sleeper, like Mule Canyon in Nevada, they can have up to 0.1%, 0.1, 0.2, 0.3% molybdenum as molybdenite. However, and I didn't discuss this, but in that extensional environment, there are no molybdenite, there are no porphyry deposits. Therefore, there's no potential for porphyry moly in that extensional environment. Of course, never say never, but the end member examples. However, in the arc examples, you can get moly present as molybdenite. Whether or not it says anything about the molybdenum potential of a deeper intrusion system, I don't know. I wouldn't necessarily say it. As I say, I've seen 0.1% molybdenum as molybdenite in deposits with absolutely no relationship to any porphyry. So, it's just another observation to make. Okay. Other questions?
Okay, great. We have those are the final ones.
Yeah.
The first one says, is it important to recognize calderas for the exploration of high sulfidation epithermal deposits?
Our caldera is important. Any structure is important. There are a few high sulfidation deposits that have been mapped out with a spatial structural relationship to caldera margins, such as radicular, very small. Look at a paper by Antonio Rivas in 1995, Economic Geology. A few others, but there's not necessarily any genetic relationship. In fact, particularly calderas tend to form in extensional environments, back arc environments. And in that case, then there's not going to be any relationship between the caldera and the high sulfidation deposits, because you don't have shallow intrusions, you don't get the environment that you do have in arcs. But any structure that's present, and of course, even calderas can then be overprinted by a migrating volcanic arc. And so it's just simply providing a pre-existing structure. So map out all structures, whether they are caldera or circular structures, because at Kimsacocha, the word caldera was not used there, more of a cauldron. It was a large eruption resulting in collapse. So the question is, should caldera be applied or not? I'm not sure. But map out all structures. Also, the basement structures at Kimsacocha, Loma Larga are very important. North-south, northeast, southwest structures were very important to controlling the focus of the deep intrusive system, the location of the diatreme, etc. So whatever the origin of the structures, map them out. If you have a caldera nearby, well, map that out as well. Sure. But focus on structures as one layer of your geology, the lithology, the structures, then the alteration, then the geochemical anomalies, etc., etc. Each layer is important to build. Okay. And?
Thank you. Next one says, can you talk more about the origin of the fluid responsible for the sericitic alteration? Is it related to a deep intrusion?
Sorry, the fluid responsible for alteration.
Sericitic alteration.
Sorry, acidic.
Yes, yes.
Yeah, well, acidic, yeah. Again, go back to Antonio Rivas's presentation, 4th of May, and he discussed the 5 environments to potentially generate acid fluids. 5 different environments. Only one is magmatic-hydrothermal and volcanic vapors condensing. So that's the best presentation to look at all of those environments for generating acid fluids, only one of which is related to SO2 and HCl, another being H2S in the steam heat environment, etc. So that's as Antonio did. That's a whole lecture in itself, and then each environment is a whole lecture. So, but the important thing to note, certainly in the arc environment, the lithocaps, the residual quartz is being formed by the pH 1.5 acid condensate. That stage is barren. And we have to appreciate that. And often, many times, or at least parts of lithocaps are barren. For example, at Lepanto, the lithocap that's 3 to 4 kilometers away from the intrusion center at far southeast, that lithocap has 12 to 49 ppb gold in it, in the quartz alunite. It's only when we get to a proximal area within 1 to 2 kilometers that the subsequent white mica fluid was flowing and then resulted in deposition of metals, copper and gold, proximal to the porphyry. So for acid alteration, look at Antonio's lecture, and remember that the acid alteration is not related to necessary metals. As Goldfields recognized at Salares Norte, they were not worried that steam-heated alteration, that there should be any gold anomaly in steam alteration, because they knew that that's something that's forming above the mineralizing fluid level. Okay.
Okay, thank you.
Yeah.
Final question.
Final. Okay.
In terms of geometry, the main ore body is included preferentially in the
Yeah, I'm not hearing you, Nicholas.
Can you hear me now?
I can hear you now, Nicholas.
Okay. In terms of geometry, the main ore body is placed preferentially in the unconformity surface.
Sorry,
What
you faded out again. Whatever, something's happening to your mic, maybe, or I'm not sure.
Jeffrey.
Yes, Monica?
Yep. Yep. Pamela Perez asks, in terms of geometry, the main ore body is in place preferentially in the unconformity surface or in the feeder. What does it depend on?
Okay, well, yeah, good question. Geometry of the ore body. Well, it depends on the geology. At Summitville, the first well-described high sulfidation deposit, it's hosted by a dome. Fractures cutting through this big dome, and there's no permeability, no lithologic permeability. So the ore body is only in fractures, high angle fractures, no lithocap developed. Whereas in other situations where you have a lot of permeable lithology, whether it's like at Kimsacocha, Loma Larga, if it's Lapilli-Tuf, etc., then you might have a lot of lateral permeability. But even when you have lateral permeability, every prospect deposit I've looked at, the best grades are in the feeder zones, where the fluids are coming and starting to depressurize, maybe boil, before they enter into the lithocap permeable horizon, where they're perhaps being diluted and possibly causing gold deposit. So always proximal to the feeder zone is the best grade. And as I mentioned before, there may not be any lithocap if there was no permeable horizon for lithocap to develop. So always try to define the feeder zones, because if they're mineralized, they will have the best grades. But of course, sometimes they're not mineralized at all. But it's only until you've found the structure controlled feeder zones and see that those are barren. If that's the case, then you can say, oh, this is a barren lithocap. Now we can drop this project. But even at Yanacocha, 1 kilometer away from some of these big ore bodies, there would be 10, 20 ppb gold in residual quartz lithocaps, just like at far southeast, 10, 20, 30 ppb gold. So find the feeder zone. And of course, the feeder zones are always related to the lithology. Is it a big fracture? Is it a caldera margin? Is it a big through-growing regional fracture? Is it a dome margin? Is it a diatreme? What's controlling the vertical permeability, the feeder zone? And then what's controlling the lateral permeability, if there is any? Okay.
Okay, Jeffrey, there is another question. Everyone's due to respond. It's a question from Barry Quiroz. Say, if you have, let's say, 3 different levels of paleo water tables, does that mean that we perhaps have 2 or 3 different pulses of steam heated alteration, and maybe 2 to 3 boiling levels, making our possible ore shoots more robust?
Okay, well, yeah, that's sort of a complicated question about levels of paleo groundwater tables. Now, one thing we know, although I said these systems form in a short period of time, they still have a certain period, several, potentially they're active overall for a couple thousand years. And during that period, commonly you can erode the, not the whole surface, but you can erode the drainage areas, the streams. And eroding a stream, which is controlling the paleogroundwater table, eroding that stream by 10, 20, 30 meters will cause the groundwater table to collapse. Now, if you get a volcanic eruption, you could fill in the stream and cause the groundwater table to move back up. So we see a lot of evidence, certainly for falling groundwater tables, but also for sometimes rising groundwater tables, basically cycling. And if you have that cycling up and down, then yes, it's possible that you could be getting different imprints. I mean, different periods of gold mineralization at different levels in the system. If you get just continuous erosion of several hundred meters, like Stuart Simmons documented in his 1991 paper at Fresnillo in Mexico, as much as 400 meters of erosion in the Fresnillo district. Well, that could be one reason for why we see such large vertical intervals. At first, we started to get mineralization at a shallow level when the paleogroundwater table was shallow, but as the paleogroundwater table fell, then the mineralization level also followed that. So again, case by case, project to project, district to district, there are numerous different possibilities, and we have to look for evidence for different paleogroundwater tables. Their steam-heated zones are easy to erode, but the chalcedony that forms at the paleogroundwater table is more resistant, like we saw at Peru. It formed a nice resistant horizon. And so oftentimes those are preserved, and that's what Stuart Simmons mapped when he was in the Fresnillo district. And just an aside, the group that made the recent discovery in the Fresnillo district, Peter McGaw's group, they basically used Stuart Simmons' 20-year-old or more mapping of the paleogroundwater tables to decide what's the likely depth that they have to drill to get to the top of the ore body. Because Stuart had shown that you need at least 200, that the ore bodies, tops of ore bodies form at least 200 meters or so below the, in that district, the tops of ore bodies formed about 200, 250 meters below the base of the water table. Again, for that district, not necessarily everywhere else. At Peru, the top of the ore body was perhaps only a few tens of meters below the steam-heated horizon. So, yeah, good question, very involved, and it could be a whole complete lecture of itself with several examples.
Okay, Jeffrey, this is the last question.
I thought I heard the last question about 5 questions ago.
Yeah, it's because it's a lot of questions.
Yeah.
Well, Franco asks, how can you explain siliceous gold-bearing banded quartz veins in the middle of central parts of intermediate sulfidation veins? We see this feature in Patagonian epithermal polymetallic deposits.
Yeah. Okay, I got the second half, but what was the first part? How do you explain?
How can you explain siliceous gold-bearing banded quartz veins in the middle of central parts of intermediate sulfidation veins?
Yeah, I think you mean, yeah, just multiple bands, mineralized bands. Well, we recognize in epithermal deposits around the world that they commonly are not a single event. We don't just get opening, quartz, and gold. Commonly, there's multiple openings. You can imagine every time there's a band, that is reflecting one period of quartz deposition and perhaps metal deposition, but each of those events probably associated with a single earthquake. And a large structure, whether it was a strike slip movement or a dip slip movement, there was big movement opening a fracture. There would have been an earthquake associated with it. At the time, Rick Simpson has published on this. He calls it the fault valve mechanism of fractures. Now, he's interested in fractures. He's a structural geologist, but that's basically explains these multiple vents forming, multiple events forming different bands in epithermal veins. I'm not sure if that answered the question, but at least we see multiple bands and it's multiple earthquakes forming during the life of the system. Okay.
Okay, that's it, Jeffrey. I think we covered almost all the topics asked by your attendants. Thank you again. Great presentation.
Yeah, a lot of good questions. Thank you.
Yeah.
But hopefully we can continue this again some other time with some other style of presentation. Thank you, Monica, and thank you, the whole Bogota team, Nicolas, and everyone else that's been involved, and also all the attendees for listening, and also some good questions.
Okay,
I see we've lost about half of the participants, but about half of the participants are still there. They're still hanging in. So have a good afternoon, and I think now here in Ottawa, it's about 1/2 beer time.
Okay, for final, thank for accepting this invitation and share of this knowledge with us. It has been a pleasure and a great contribution to our community. Thanks a lot.
Thank you.
And also thanks to Dini. Thanks, Dini, from SEG for hosting this 2-hour conference. It seems like Nicholas had problems with his micro. We offer apologize for that.
Yeah, no problem. That happens.
Gracias a todos por su asistencia. Esta conferencia estará disponible próximamente en el canal de YouTube Cuarentena con Geociencias. Está en la playlist SEG SGA, al igual que todos les hemos realizado hasta el momento una grabación y ha sido subida a este canal. Hasta una próxima oportunidad y que estén muy bien.
Muchas gracias, todos.
Thank you. Muchísimas gracias.
Okay.
Hasta luego.
Luego. Bye.